So imagine handing a state-of-the-art coding AI a 10 million token transcript of its own execution failures.
Right, just a massive unreadable wall of text.
Exactly. You point at it and expect the model to just, autonomously debug its own scaffolding. But it simply cannot do it.
Yeah, it either hallucinates a fix that breaks something else entirely or it just gets completely lost in the noise.
Right. So today, in our deep dive, we are looking at why the smartest language models on Earth are fundamentally blind to their own operating environments, and how a new framework actually solves this observability crisis.
It's a huge shift in how we think about agent architecture.
It really is. Because, for you listening as a practitioner in machine learning and data science, you are already intimately familiar with the scaling wars.
Oh, absolutely.
We obsess over parameter counts, pre-training compute, subtle transformer tweaks. But if the base LLM is the engine of a race car, the surrounding harness.
Right, the tools, the middleware, the memory integrations.
Exactly. That harness is the transmission, the steering, and the chassis. So dropping a massive GPT 5.4 DeepSeek V4 engine into a handcrafted, brittle chassis.
It's not going to win you any races on long horizon coding benchmarks.
No, it won't. And that architectural mismatch is really the defining bottleneck of current autonomous agent research, right?
It is. Handcrafting these harnesses is just, well, it's a dead end. We're stuck in this paradigm where human engineers have to manually inspect massive unstructured trajectories.
Which takes forever.
Right. They have to identify recurring failure patterns and write custom Python patches for a specific middleware hook or, rewrite the system prompt over and over.
And given the rapid iteration cycle of base models, we're seeing Qwen 3.6 Plus or Gemini 3.1 Flashlight dropping almost monthly.
Exactly. Manual engineering mathematically cannot keep pace with those model capabilities.
So that brings us to our mission today. We are unpacking a highly technical paper from researchers at Fudan University, Peking University, and Shanghai Zhiheng.
Yeah, the paper is on Agentic Harness Engineering, or AHE for short.
Right, AHE. And they propose a fully automated, observability-driven evolution loop that optimizes the entire scaffolding of a coding agent.
Which is a massive leap from what we have now.
Definitely. But to understand why AHE is necessary, we really need to look at why current automated baselines fail. The industry already has methods like ACE, right?
Yeah, ACE relies on generating in-context playbooks.
Right. Or TF-GRPO, which uses trajectory feedback reinforcement. So why don't these existing methods work when you try to optimize a full heterogeneous harness?
Well, it really comes down to entangled action spaces and the credit assignment problem.
Okay, break that down for us.
Sure. So TF-GRPO and similar reinforcement mechanisms typically target a single editable surface. That's usually just the system prompt or maybe a highly constrained skill library.
Right.
But when you ask an optimizer agent, which, by the way, is perfectly capable of writing complex C++ or Python code.
Yeah, I know it can code.
Exactly. When you ask it to edit its own harness, it faces a massive observability bottleneck.
Wait, I need to clarify this. If the model has the capability to write a complex C++ script from scratch, why is rewriting a simple Python middleware script a bottleneck?
That's the core question, isn't it?
Is it a capability issue with self-reflection, or is it strictly an architecture problem?
It is strictly an architecture problem. Existing harness frameworks are tightly coupled.
Meaning everything affects everything else.
Exactly. Let's say the agent tries to modify a file read tool to add pagination because, it keeps hitting context limits.
Makes sense.
In a standard setup, doing so might inadvertently break the parsing logic in the middleware, or it might contradict an instruction hard-coded into the system prompt. The agent just cannot safely isolate its edits.
Ah, okay, so it's walking through a minefield.
Right. And furthermore, the feedback it receives is completely monolithic. Long, unstructured execution trajectories easily span millions of raw tokens.
Which brings us back to that 10 million token transcript issue.
Precisely. The actionable signal, like the exact moment the file read tool caused a memory overflow, is completely buried.
So an evolution agent can't parse a wall of raw terminal outputs and API calls to map a downstream failure back to a specific line of code.
It just can't, not reliably.
Okay, so if the agent cannot isolate the fault because everything is tangled together, it obviously can't engineer the fix without massive collateral damage.
Exactly. which leads directly into the paper solution.
Right. The authors solve this with what they define as 3 observability pillars. Let's break down the mechanics here, starting with pillar 1, which is component observability.
Yeah, and this relies on a framework they call NextAU.
NextAU, how does that work?
NextAU fundamentally reorganizes the harness into 7 completely orthogonal file-level component types.
Okay, so it's physically separated them.
Yes, it maps the architecture into explicitly separated files. You have the system prompt, tool descriptions, tool implementations, middleware, skills, sub-agent configurations, and long-term memory.
I understand the theory of decoupling there. But how does the system handle the actual version control autonomously?
Well, because these are explicit, physical files mounted in a sandboxed workspace.
Right.
Every logical edit the Evolve agent makes translates directly into a standard Git commit.
Oh, wow. So it's actually using Git under the hood.
Exactly. The framework is programmatically executing git diff and git commit commands.
So if every failure pattern maps to a single component class, say editing the tool implementation file instead of the system prompt,
Then if an edit fails validation, the system does not rely on the LLM's context window to quote-unquote remember what it changed.
just rolls it back.
Yeah, the overarching framework simply executes a deterministic git revert to the previous commit hash. It completely sanitizes the action space by providing native, flawless revertibility.
That is incredibly elegant. Okay, so programmatic version control handles the action space. But let's tackle pillar 2, which is experience observability.
Right, because we still have to address that 10 million token nightmare.
Exactly. The paper introduces an agent debugger to compress the trajectory down to roughly 10,000 tokens. But I struggle with this concept from an information theory standpoint.
Because of data loss.
Yes, exactly. Compression inherently means data loss. If you distill 10 million tokens down to 10,000, aren't you inherently risking the loss of the critical bug's context?
That is a very valid concern.
Like, how do we know the heuristic algorithm isn't filtering out the exact API call or reasoning step that caused the failure?
Well, the authors circumvent that by not summarizing the trajectory linearly. The agent debugger does not ask an LLM to read the whole log and write a summary.
Oh, so it's not a semantic summary.
No, not at all. Instead, it treats the execution history as a navigable, structured database. Think of it like a black box flight recorder.
Okay.
And the agent debugger is the NTSP investigator.
Huh.
The investigator doesn't listen to the entire flight audio from takeoff to crash.
Right, they look at the point of impact.
Exactly. They parse the final crash state, the exception or the failed assertion, and heuristically work backward. The agent debugger isolates the specific API calls, terminal outputs, and intermediate thoughts that immediately preceded the failure node.
Ah, so it builds a causal graph.
Yes. It organizes this deterministic graph into layered, drill-down evidence reports. So those 10,000 tokens are a highly targeted causal slice of the execution graph, not a fuzzy semantic summary.
I see. It extracts the causal chain of the error state, which allows the Evolve agent to consume the data without blowing out its context window.
Which perfectly sets up pillar 3, decision observability.
Right. Decision observability, which relies on a change manifest. Walk me through a micro example of how the Evolve agent actually formulates and tests this manifest.
Okay, so the manifest acts as a strict falsifiable contract.
A contract, okay.
Let's say the Evolve agent analyzes that NTSB-style evidence report and realizes the base agent failed a task because a bash script timed out waiting for a user input prompt.
A classic hang.
Right, so the Evolve agent modifies the execute bash tool implementation to automatically append a non-interactive flag to every command.
Makes total sense.
But before that commit is accepted into the main harness branch, the agent must generate a manifest stating, quote, I predict this modification to tools.py will fix task 45 by preventing interactive prompts.
So it has to stake a claim on the outcome.
Exactly. The system then independently reruns task 45. If the task still times out or fails for an entirely different reason,
The hypothesis is wrong.
the falsifiable claim is proven mathematically false, and the system immediately triggers that git revert mechanism we discussed in pillar 1, rolling back tools.py to its previous state.
Wow, so this stops the loop from devolving into chaotic trial and error entirely.
It forces the model to stake its edits on a specific, testable hypothesis, rather than blindly mutating code and just hoping for a higher overall benchmark score.
That's brilliant. But, theory is cheap in AI research.
Yeah.
I want to see what happened when they forced this autonomous loop to actually solve complex problems.
Let's look at the empirical results then.
Yeah, let's look at Terminal Bench 2, which is an 89-task, multi-hour workflow benchmark.
The quantitative results on that benchmark are highly definitive. Over 10 iterations, the AHE loop lifted the pass-at-one rate from 69.7% to 77.0%.
That's a solid jump. How does that compare to human baselines?
For context, a human-designed Codex-CLI harness achieved 71.9%.
So it beat human engineers.
It did. And the automated baselines, ACE and TF-GRPO, scored 68.9% and 72.3% respectively. AHE systematically evolved a basic bash-only next-in-the-U zero seed into a state-of-the-art framework.
Okay, evaluating on the training distribution is one thing, but as you know, the true test of any scaffolding is cross-benchmark transfer.
Absolutely.
So they took the frozen AHE harness, right? No re-evolution, just the exact files optimized for Terminal Bench 2, and applied it to SWE-bench-verified.
Which consists of 500 tasks across real-world GitHub repository.
Right. How did it do there?
The frozen AHE harness topped aggregate success on SWE-bench at 75.6%, compared to the unmodified seed at 75.2%.
Okay, a modest gain, but...
But the crucial metric you have to look at here is the token efficiency.
Oh, interesting.
The frozen AHE harness achieved that state-of-the-art success rate while using 12% fewer tokens than the baseline seed.
Wait, I need you to unpack the mechanics of that. How does a harness execute a more complex, generalized workflow while consuming 12% fewer tokens?
It comes down to where the behavior is actually encoded.
Okay.
Methods like ACE and TF-GRPO rely heavily on bloating the system prompt. They inject terminal-specific playbooks and massive instructional blocks directly into the context window.
Ah, I see. So when you apply that bloated prompt to a completely different task surface like SWE-bench...
You waste massive amounts of tokens on irrelevant instructions, which actually degrades performance.
Right, because it's reading a playbook for a different game.
Exactly. AHE, conversely, encoded the new behaviors directly into the tool implementations and the middleware Python scripts.
Oh, that's smart.
So the base model does not have to read a massive prompt and rederive the tool strategy on every single inference call. It simply calls the optimized Python function.
Which proves the structural changes AHE makes are fundamentally more generalized and compute efficient.
Exactly.
And that dynamic perfectly explains the asymmetry in the cross-model transfer data, doesn't it?
It really does.
Because the entire harness was evolved using GPT 5.4 on the high reasoning setting. But when they applied this frozen harness to completely different model families, DeepSeek v4 Flash saw a massive plus 10.1 percentage point gain.
Yeah, a huge leap.
Qwen 3.6 Plus jumped by plus 6.3 percentage points, and Gemini 3.1 Flashlight gained plus 5.1.
Right.
So why does a totally different model family like DeepSeek see the largest performance jump from a structure optimized specifically for GPT 5.4's quirks?
It mathematically demonstrates the relationship between model saturation and coordination overhead.
Explain that for us.
Sure. Consider a highly capable, highly saturated base model, like GPT 5.4 High. When it encounters a complex file system, its raw reasoning capacity allows it to dynamically coordinate file reads, memory management, and tool parsing on the fly.
Even if the surrounding harness is bare bones.
Right. But base models that are further from saturation, like DeepSeek v4 Flash or Gemini Flashlight, lack the raw transformer capacity to reliably rederive that complex coordination mid-task.
Okay, so they struggle with the overhead.
Exactly. When you provide them with the frozen AHE harness, you are essentially offloading the cognitive load of memory management and tool orchestration from the model's internal weights into explicit, hard-coded Python middleware.
So the weaker models extract vastly more utility from this rigorously engineered external structure.
Because it perfectly compensates for their internal reasoning deficits.
That is fascinating. So the evolved components encode universal software engineering methodologies, not just overfitting to one model.
Yes, but we need to isolate the variables to see where that value actually lives.
Right, the ablation studies. The authors swapped individual files from the evolved AHE harness back into the baseline seed one by one.
And the ablation data unequivocally showed that the performance gains live entirely in the structural components. Long-term memory alone yielded a plus 5.6 percentage point gain.
Wow.
The tools yielded plus 3.3, and the middleware yielded plus 2.2.
And what happened when they swapped in the evolved system prompt by itself?
It actually regressed performance by 2.3 percentage points.
Wow, a regression.
Yeah. Prose-level strategy in a prompt overfits wildly to the specific syntax of the training tasks. Factual, structural changes in code logic transfer universally.
Okay, but I have to challenge the math here because the non-additive limits do not add up.
They don't?
All right, if long-term memory is plus 5.6, tools are plus 3.3, and middleware is plus 2.2, those single components sum up to a theoretical plus 11.1 percentage point gain.
Yes, theoretically.
But the full AHE system stack only gained plus 7.3. It is like adding 3 fantastic spices to a dish and ending up with a muddy, overpowering flavor.
That's a great way to put it.
In fact, the paper notes that on the hard tasks in Terminal Bench 2, the long-term memory component running completely alone actually outperformed the full AHE stack.
So why does combining heavily optimized components degrade the theoretical maximum performance?
Well, it's because combinatorial optimization in agent systems operates under strict boundary constraints, specifically step budgets and context windows.
Okay.
These components do not operate in a vacuum. Throughout the evolution iterations, the memory, the middleware, and the tools all independently learn to push for strict closure-style verification.
They all evolve defensive programming habits, essentially.
Exactly, to double-check their outputs. But when you stack them all together, the agent gets trapped in a cycle of over-verification.
Oh, I see.
It spends its precious long-horizon step budget executing redundant rechecks. Since the Evolve agent optimizes for an aggregate benchmark score heavily dominated by the 55 medium difficulty tasks, it converges on a local optimum.
So the heavily verified stack works beautifully for medium complexity. Right, but it completely exhausts the step budget on the hard tasks, leading to execution timeouts. It clearly highlights that stacking effective local edits does not guarantee a global optimum.
That step budget exhaustion is a fascinating bottleneck. And if components can conflict like that, it raises a critical question about loop attribution.
Yeah, how well does the agent actually understand what it's doing?
Exactly. How well does the Evolve agent actually understand the systemic consequences of the code edits it makes?
We can actually measure that precisely by analyzing the precision and recall of the Evolve agent's self-predictions in those change manifests we talked about.
Okay, what were the numbers?
For predicting what an edit will successfully fix, the agent achieved 33.7% precision and 51.4% recall.
Okay, to contextualize that for you listening, 33.7% precision means 1 in 3 of its predicted fixes actually resolved the targeted issue without breaking the primary task.
Right.
That is roughly 5 times better than a random baseline, which proves the edits are genuinely evidence-driven, not just random genetic mutations hoping to hit a higher score.
It is entirely evidence-driven for fixes. However, there is a glaring blind spot in the data.
Which is?
While the loop is highly reliable at predicting fixes, it is almost completely blind to predicting regressions.
Oh, wow.
Yeah, the agent's ability to foresee what a localized edit might break elsewhere in the heterogeneous harness is barely above random chance.
So it knows how to fix the plumbing, but it doesn't realize it just flooded the electrical panel.
Exactly. The authors explicitly pinpoint this lack of regression foresight as the most critical hurdle for future self-evolving research.
Does this lack of regression foresight tie into the operating point coupling mentioned in the limitations?
It absolutely does.
Because the paper notes the evolution was fitted to GPT 5.4 High's specific step budget and timeout constraints. What happened when they swapped in the more advanced GPT 5.4 X High model?
The system actually failed to capitalize on the better model. Yeah. The X-High tier naturally takes longer per inference step and outputs vastly more complex reasoning sequences. Because the AHE harness had evolved hard-coded timeout constraints and parsing rules specifically fitted to the high model's cadence.
It choked on the new model.
Yes, it forcefully truncated the IXA model's trials. It conflates the true cross-domain portability of the harness with a brittle coupling to the specific operating point parameters of the original hardware and model tier.
Let me synthesize this. The agent is practically blind to the regressions it causes, and the evolved structures mathematically overfit to specific inference latencies and step timeouts.
Right.
So this methodology is nowhere near ready for unchecked production deployment, is it?
It is absolutely not ready for unchecked deployment. And the authors are incredibly transparent about this.
Good.
AHE lacks the comprehensive guardrail stack required for long horizon cleanup, cost control, and misuse prevention. It does not have the robust mechanisms required to safely govern recursive self-modification in a live production environment.
So it's a proof of concept.
Exactly.
Yeah.
It should be viewed as a highly successful, tightly controlled research prototype that proves the mathematical mechanics of observability-driven evolution. It is not an autonomous software engineer you can safely unleash on a production code base.
Let's summarize the architectural journey we've mapped out today. Agentic harness engineering proves that by abandoning unstructured trajectory reinforcement,
And the millions of tokens of noise.
right, and instead transforming the agent's action space into explicit, observable, and falsifiable file-level contracts, we can systematically evolve scaffolding that outperforms human design.
Which is a huge milestone.
We've seen that structural edits to tools and middleware transfer highly efficiently across different benchmarks and entirely different model families, while hyper-optimizing prose and system prompts is largely a dead end.
And when you look at the broader landscape of machine learning, there is a profound economic implication hiding in these transferability results.
Oh, absolutely.
We just discussed how hard-coded, evolved harnesses provide massive performance leaps to smaller, less saturated models like Gemini Flashlight or DeepSeek.
Essentially compensating for their transformer deficits.
Right. Historically, companies have aggressively open-sourced their model weights while keeping their proprietary infrastructure closed. But if the real generalized value and the true competitive advantage in autonomous agents lives in the structural middleware and the memory architectures.
We may see a massive paradigm shift in open source economics.
Exactly. We might soon enter a world where massive foundation model weights become heavily commoditized and practically free.
While the highly evolved, mathematically optimized scaffolding architectures become the most closely guarded, premium intellectual property in the AI industry, an entire industry pivoting from protecting the engine to fiercely guarding the blueprints for the chassis. It completely reframes where the actual leverage in machine learning lies moving forward. And that is a fascinating economic inversion for you to mull over as you optimize your own deployment pipelines.